let's talk electric force. Let us imagine for a moment that we have two protons, for example. And what we said earlier is that light charges will repel, so these will actually move away from each other. Or if I have a positive charge and a negative charge, then these will attract each other, and then they'll actually move to get towards each other. Now what we actually have here is, because these are still and they're moving, we have a force. Well, we have an acceleration. Because they were still, then they speed up. And acceleration is equal to force divided by mass. So what that means is, if you have two charges, either the same or different, there's going to be acceleration. That means there must be a force, because a force is what creates acceleration. That's Newton's second law. Force is equal to mass times acceleration, which is just that rearranged. So that means, how can we tell how big that force actually is? And what we actually have an equation for this. This is for electric statics. Force is going to be a force. Force is measured in newtons. Is going to equal a constant times Q1, Q2. So these are charges. And charges are measured in coulombs over r squared. So this is the distance between the two, or the sense of the two. That's measured in meters. And so how big is this, and how big is this force? Well, that force depends on those, and K. And K has been measured. K is a coulombic force. K in this case is equal to 8.988 times 10 to the 9 newtons meters squared per coulomb. That big C. So let's actually do an example. Let's do an example 4.2 from the notes. What is the force of an electron on another electron at 1 meter, and at a distance of 1 nanometer. Now, I'm a great fan whenever doing problems. Step one should always be draw a picture. So we have an electron and we have another electron, and the distance between them is going to be 1 times 10 to the negative 9 meters. Remember, that's 1 nanometer is 1 times 10 to the negative 9 meters. So actually, let's write down what we know. What do we know? We know Q1 is equal to an elementary charge, which is equal to 1.602 times 10 to the negative 19 coulombs. We know Q2 is also an element, and that's going to be negative because that's an electron. Q2 is another electron, so that's also going to be negative 1.602 times 10 to the negative 19 coulombs. And we know R, the distance between them, is going to be 1 times 10 to the negative 9 meters. So we can now write this out as an equation. We're using our Coulomb's equation. Force is equal to K, Q1, Q2 over R squared, which is equal to, well, we know from earlier that K is equal to 8.988 times 10 to the negative, 10 to the positive 9 Newton meters squared per coulomb squared, times Q1, which is what, negative 1.602 times 10 to the negative 19 coulombs, times Q2, which is equal to what, negative 1.602 times 10 to the negative 19 coulombs. And we draw them all over R squared, so that's going to be 1 times 10 to the negative 9 meters squared. Now, what we're going to do is just, at this point of the cycle, we just stick it into a calculator. So we've got 8.988 x 9. If you use that key, the EXP key, means you don't have to go times 10 to the power of 9. It does it all for you. Times negative 1.602 exp negative 19 times negative 1.602 to the power of negative 19 divided by 1 to the power exp negative 9, and that's going to be squared equals. So if we do all of that and stick that through, that's going to equal 2.307 times 10 to the negative 10 newtons. And now we have to ask ourselves the question, is that a little or a lot? Does that seem reasonable? And the thing is, well, yeah, I mean, the thing you have to remember about these is electrons are not very heavy. They're like 10 to the negative 30 something kilograms, so that's actually a very big force on electron. And a force on electron, you'll notice that this actually sort of, this equation here that we're using, actually very similar to the gravity equation. Force is equal to Gm1m2 over R2. So R squared. So I mean, these equations work in a very, very similar way. And I mean, as I was saying earlier, electromagnetic force is one of the fundamental forces. Gravity is another fundamental force, and there's also the strong and the weak force as well. The difference, one of the big differences between these, this works on mass, this works on charge. This is always positive unless you have a negative mass. The force is always going to be positive. This can be positive or negative. Notice I end up with a positive number here. That means it repels. If it was a negative number, this would attract. But you don't have to remember that. All you have to do is look at the picture and go, oh, those two are going to be trying to go away opposite directions because like charges repel. So actually, let's just check this. Let's just check the size of this force compared to the gravitational force between these two. This is exercise 4.3, I believe, which is, and so the question here is, what's the force of gravity on an electron? What is the force due to gravity? Gravity on an electron 1 nanometer away from another electron. Another electron. So basically this is exactly the same problem up here, except now instead of electric field we're dealing with the gravity between them. So we're going to use the universal law of gravitation. G is equal to m to r squared. We then go G is, what's G equal to? 6.67 times 10 to the negative 11. And that's going to be meters cubed per kg per second squared. That's gravitational constant. Times, well, what's the mass of an electron? The mass of an electron is 9.1 times 10 to the negative 31 kg. That's for that electron. Remember, for gravitational force is always attractive, and it's between any two forces in the universe, so we're going to take the other one up here, which is 9.1 times 10 to the negative 31 kgs, and then we're going to divide it by the distance between them, 1 times 10 to the negative 9 metres. Notice it says squared there. This is one of the most common errors with people doing this. They forget to square that bottom one. So let's work out what the gravitational force is. 6.67 x negative 11 times 9.1 x negative 31 times 9.1 x negative 31 divided by 1x negative 9 squared equals 5.523 times 10 to the negative 53 newtons. So what can we tell about this force? The electrostatic force was 2.307 times 10 to the negative 10 newtons. The gravity force is 5.523 times 10 to the negative 53 newtons. So this is basically what, 2.5 times 10 to the 43 times bigger. So this electrostatic force is significantly bigger than the gravitational force between these things. And where do we see this actually occur in real life? Occasionally, I mean the classic ones are gold leaf, or electrostatic charging. So if you have a person, the classic one is you have a person, if you stick them on a Van de Graaff generator, then their hair will stand up on them, because basically the hair ends up with charges, not a lot, but enough, and they will repel and try and get as far away from each other as possible, so the hair will stand up. So electrostatic charges are actually used quite a lot. One of the classic ones is a spray booth. If you have a spray gun and you're spraying out droplets of paint, if you give them a negative charge, and then you're spray painting a car, and you give the car a positive charge, then these are going to attract, so that spray, that paint will be attracted to the car body, and that will greatly reduce the amount of spray paint you need, because you're going to get very little overspray. So and we use them in electrostatic filters as well. If you have, like in Huntley Power Station, if you have a big chimney, you put a grid in here. So this, if you make that grid positive, and then you actually put a grid up there, negative. As the smoke comes through here, it picks up a charge, so that the smoke becomes, as the smoke becomes through here, it becomes positively, or the dust comes through there, it becomes positively charged, and then it gets attracted to the negative walls of the chimney. So you get rid of 90-something% of the dust particles just by using electrostatic filters, just by putting a charge on the dust and then having something that'll collect out. So this type of stuff is actually used quite a lot in reality. So